Hello. In this video, I show how my studies of bird songs in the 1970s led to an understanding of a design feature in the universe. I describe its appearance in songs of the indigo bunting and in human handwriting. After we experience it with falling ping pong balls, it is applied as a model to explain the appearance of mass and gravity in the universe. Its potential to explain Einstein's relativity and shortcomings, and the appearance of paired stars and black holes in the universe is also addressed. This video is for every inquiring mind, regardless of scientific background. In many of my previous videos on YouTube, I had worked out some of the concepts that are described here. They may have appeared a bit woo-woo, but the process of finding words for new concepts is sometimes quite difficult. That had nothing to do with the fact that the first 4.5 minutes of this video are delivered with the top of my head absent. Fortunately, our hosts kindly readjusted the owl camera microphone to a better position. This presentation is in front of a familiar group of seniors, and therefore I affectionately call it my senior thesis. I hope you find it intellectually stimulating and fun.
This talk is based on science. It's answerable to science, but it's not science, it's philosophy. It is a possible solution to something that is a very complex question. Let's go to the beginning of the story. It starts with Kathy and I in Hawaii, on the island of Hawaii, the big island, and we're going up Mauna Kea, and we're going to see the observatories, 13,000 feet something, and 13,000 feet can take effects on the human body, but that's a story for another time. So, but what was important about it, even though the observatories were closed, was that the guide took out a telescope with a lens about this big, just huge, and he pointed it up to the night sky, and he showed us two stars that were kind of close to each other. One was red and the other was blue, and these were paired stars. Why was one red and the other blue? Everybody but Bill can try to answer this because he already knows the answer as being a physicist. Why would the light from one star be red and another star be blue? Yeah, it's the light wave frequencies. Even if they're giving them off at the same frequency, if one is moving away, it's going to make it seem like it's longer, and the other one's going to seem like it's shorter. So these were paired stars, and the first time I'd ever seen any. And it turns out that approximately 85% of stars in the Milky Way are paired stars. They go around a common center of mass. Notable examples of these, and I think these are probably the ones I saw, were Cygnus 1, and the other one is Sirius. So now you can say that Ken Shiovitz gave a serious talk. Okay, I'm going to start at the end. This happened just a few months ago. Somebody put in my theories into artificial intelligence to find out something. I made a comment. The person who's a physicist and is working a lot with AI put it in, and AI kind of liked what I was saying. And what I was saying, I asked the question, by the way, has anyone wondered why stars are now apparently black holes, what's in the middle of a galaxy? Why do they so often occur in pairs? And I'm going to be talking to you about my coil theory. And my coil theory addresses this. I say that moving energy would likely need to have partners in order to come up with this, and doing reflections by partners in order to make a stable stereotype structures that are going around each other. And the coils will be the basis both for the black holes and for particles. By connecting, they'll become particles. Now, I'm going to talk about all this later. Basically, it liked what I was saying, and its last statement is it's an important insight and certainly worth keeping in mind when considering the broader organization of astrophysical systems. Now, I understand that AI sometimes can tell you nice things. All right, now how did I come up with that from birdsongs? Well, let's go to birdsongs and see the indigo bunting that I was studying. Eastern coast of the United States, western half of the United States is a largely bunting. I took and modified it, and then my wife, the artist, painted it to look like a largely bunting. Why is that important? Because when I play the song in the bird's territory, they will defend against the bird that they see. And my indigo bunting got so beaten up that I can't show it to you today, because they will start out by attention and this is an intruder into their territory. So then they will get closer, or get attraction, and then pretty soon they'll do a display which looks like that. That's the wings. They're just, right in front of its face. Most of the time, the singing of the song communicates, it's my territory, I'm tough, here I am. It's different than calls that say danger from above or danger from below, or I want to mate with you, or sure, come on. Those are some of the calls that are very short. The songs are more extended. And I will play you an indigo bunting in what your song, and what you're seeing on the screen is the sound spectrograph, the sonogram of the indigo bunting song. And the sonogram is going from low frequency to high frequency. So if I did a trace over time, it might look like that would be about 1/8 speed or something. Indigo bunting song actually is much faster than that. And I will do some sounds in pairs. You see there's different shapes. You see the different shapes? Those are syllables. I have about 100-ish, over 100 different kinds of syllables. And the syllables are a behavior that are formed by the muscle movement. So you really can think about it, muscles affecting the air, and muscle movements making it go slower or faster, making it go up and down. The syrinx actually has two sides to it, so they can do. I'll just do it for you at 1/8 speed.
Wonderful.
Thank you. They can tell individual singers at a distance by what the pairing pattern is. So sometimes it's a 2, 2, 2, 2, 2. Sometimes it's 2, 2, 2, 2. Some of these have like 4s and 3s in there. So a bird can tell by the rough information, and also can tell by the fine structure. And I did a lot of study on the fine structure of the birdsong. The syrinx can make sound. They can do this part with one side of the syrinx and that part with the other side of the syrinx. The syrinx is like the larynx. Only it's down just a little further. So the other thing about birdsong is it's a behavior. You can sound spectrograph it, you can take out a ruler, and you can measure it. And so when you measure a birdsong, you're measuring something that's going on with the behavior over time. And by the way, I found kind of a periodicity of sounds. If one was 9 milliseconds between the inflection points, and some of them might be 18 milliseconds, 27, 36. It wasn't as neat as that, but I found that 9 milliseconds was like an important number. So there's something going on with the time. And then I started to take sound out. This is a 1/8 speed. So I took out sound and I replaced it by silence. And I did different patterns of that. And here's what I found, that if you did the 2 in a row and then another 2 in a row, they would display to that. 2 in a row and then take out a full one, they would display to that. If you did this 1 and took out 1 and took out 1, they would display to that. But when I had this very close to the 9 millisecond periodicity, if you took out every other one, there was no display. So the timing has very much to do with how they recognize it. I thought, well, let me find out some more. And then I went to my postdoctoral work in Montreal. This is my doctoral work. And then some of the stuff I did at the University of Michigan, Dearborn. And then I went to Montreal and I'm using a bird as a pointer. I did try to do something that covered the spectrum of the bird song with all sorts of different variations, making artificial bird songs, and to see if I could do something that wasn't in their alphabet, the exact shapes, but something unique to see if they responded. And I got up in the middle of the night, used the machine at this college department, and this went on for weeks and weeks until I was absolutely weird. And I went out into the field and I played bird songs, and what did I find on the first day? They weren't going to respond to any. So I went back, drove back from the biological station located halfway between Ottawa and Canada. I drove back to Montreal and I stayed up all night and I made this syllable right here. I did that syllable and I went back and I tried it and I got a response. I was in the middle of nowhere and they responded. And I thought, oh my God, I wish somebody had seen that. And all of a sudden, this person comes out of the bush. And I said, I didn't say, what are you doing behind that bush? I said, did you see that? And he said, yes. And I said, what are you doing behind that bush? And And he said, I'm from New Zealand and I'm walking across Canada. And he just happened to be there at that exact moment. Anyway, the closer I got to the exact real shape of the syllable, the stronger the response. And so it's kind of like, you know that when you're a baby, you're not going to end up barking like a dog, hone in on human parameters, but you have to learn actual shapes. I think my major professor was working on it, my doctoral advisor, I mean, and he suggested that bird. And it's also because I had this alphabet of stereotyped sounds. And for my master's degree, I went to different states and I found out that the birds in Kentucky had like a 90% overlap with the birds in Michigan and New York also. So it was very good. The important thing is that time-based configurations endure because they work. And when we get to the universe, and I'm going to start talking about that, I want you to remember this. This is a lot more control systems going on with the birds, but it's going to be basically the same principle.
The response that you get is similar to your making noise and they respond equally or what?
You mean people? Are you talking about my artificial syllables? There's the different levels. The highest level was attack. The closest next one was this display. The next one was attraction. The further one was attention. They basically paid attention for a second, and then that's all. There's something. They could tell it wasn't an indigo bunting. Yes. Yeah, that was because the only difference between that and this was that this one's in their alphabet of syllables. Okay, so now this leads us to the design feature of the universe I was talking about, controlled loitering. That is the sound itself, instead of all the details about what it is, that they have evolved a system whereby by taking sound and expanding it over time, they were able to do things with it and find and make stereotype things or things that were useful. And the ones that are most useful stick in their alphabet. So I will be hitting you with loitering until ping pong balls are dropping out of your fingers. When I talk about controlled loitering, I'm not talking about conscious control necessarily. Your body has control of a lot of things. Your smooth muscles do things that you don't, when you got to go, you got to go. There's a lot of things happening that aren't necessarily conscious, but they enter your conscious. I'm defining loitering as extending the time spent in a patch of space. That is, there's movement, and no matter what happens to the net movement? It's the net movement of loitering. Right now, it's in the news an awful lot about loitering munitions, drones that are hanging around a spot. I know it's a rough subject to talk about here, but it's because the word loitering is actually very legitimate. We think of loitering as a kid in the lunchroom hanging around with the opposite sex or whatever sex that they're interested in and spending time with them instead of moving along. And when I talk about control of loitering, I'm talking about either slowing the speed or taking a longer pathway to get there. Instead of going as fast as possible, if you're not going as fast as possible, you're loitering. Think of slowing speed and complexity takes to slow speed versus taking a longer pathway, which is kind of a more simple way to do that. I'm going to give you an example whereby hopefully you'll remember this when you're thinking about what loitering is. You got two twins. They're hanging around the lunchroom just talking to people, and they're both loitering. They're both equally fast, and I say to one of the twins, okay, I want you to go from where we are to the other door in the lunchroom as fast as you can. And I say to the other twin, I want you to go as fast as you can, but I want you to go around every table in the room before you get to the end. And so you say, 1, 2, 3, go, and who wins? The guy that's not loitering. The other one was taking a longer pathway. Okay, and that's going to come to play when we get into the universe. Because I want you to have this cemented in your mind, I need you guys in this volunteer to drop a ball into a bucket. Okay, you have a really good lungs, so you be the blower guy. And behind you, come on, you be the dropper. Now you got 6 chances here. But not to do the simple one. This is
We
just,
gotta drop it.
okay, all you're doing is just so everybody can see you. So come around here just a little bit more. Okay. Now you are just gonna drop that in. See it?
You're gonna glue it.
No, I'm not gonna do that. Okay, perfect. Okay. You don't need anything for that. If you want to win all the ping pong, you have 6 chances to do this. Ted, stand up. Yep. And you are going to blow the ball. He's going to drop from the exact same spot, and you're going to blow the ball. And he's going to take a loitering path.
Wait, I'm gonna drop it here.
No, you're going to drop it just like you did before, and he's going to try to blow it into the path and making the path longer. Okay, well, you got 5 more chances. All right, now you understand about the blowing, and that's basically what the birds are doing when they're making a bird song, is they're blowing by contracting muscles and making the sound last longer.
Take a deep breath.
I can see, when they're going, you can see the mouth move. I don't know if they go, but they do, and their airflow is a little bit different, but it's basically the same thing, but they can keep it up for a whole lot longer than we can do.
Pretty good.
Yeah. They have a syrinx instead of a larynx with the vocal cords. They have a syrinx, which sits on both ends. You know how your trachea goes down and breaks into bronchial tubes? It kind of sits around the break, so it's 2 sides can act. Now, you guys think you're getting away easily. Come on, stand up. We're going to do loitering in handwriting now. I want both of you to make a capital D, but do it backwards so it will look like it's forward for now. Okay, interesting. First thing you notice, definitely took them less time to go down than it did the loitering. The other thing you might have noticed is they were hitting control points. They started there, they went down, do that, went back up again, and then I think Carl did the same.
The second time I took out the extra movement.
Oh, okay, you got more.
But then I had to think about it because then I had to start from the bottom.
Okay, so on this target, stay up there because I'm going to need you for some more letters. They're loitering during this period where they're not going straight, but you see that little bit of curve? Where did that come from in evolution? That little curve. If you had something falling, maybe make a capital L so they could see it. Okay.
I see it sing.
That's right. That was exactly how we saw it. And you notice that they did the sharp control point that went over. Sometimes when you're in a hurry, though, people will do it more lazily. There's different letters when you get to handwriting. You're doing that all the time.
You meant block letters, not
I know.
script,
Exactly
right?
You did. How is it that you could write your letter backwards? You have it up here at the control point. You have it up there, the control point, and you're supposed to go that way. How do you know you can just do it the other way? Okay, you can. Because if you break it down, it's a bunch of control points and a bunch of loitering, and then you just tell it what direction. I'm writing Ken like that. I can also write Ken like that. So you have the whole plane. But I'm particularly interested in going in and out of loitering. You notice this is going down as fast as it can, and then it's going through, it's this loitering, but during that going down, there's a little bit of a curve, and there's another little bit of a curve, and I call that the onset and the offset loitering. And in the other direction, it's the other way. You see where I'm heading toward? Making handwriting then as evolving those little curves into a control system that allows you to make the curve instead of the sharp always that you're able to do a loitering curve. Showing you the birdsong here, you're going down as fast as possible, and then it starts to loiter. How it got fatter? That was just a figment of the old sonogram. That's how they work. They just were fatter when they're going straight and skinnier when they're going down. So that works with onset and offset. All right, you guys, make an O for us.
Which way?
You.
That was a full
Dealer's choice.
question.
Okay. So it's all loitering. Where you started to where you're going, then you got back to that control point. So there might be a control point here too. In this tofu, I have the 4 control points. Now, make your O very, very small. All right, you can do that. You can take the same instructions for making the big letter, you can make it a small letter. Why? because it's a combination of the loitering signal, is it outside loitering or is it inside loitering? It's like, if you made an O with inside the loitering, it would look like that. It would look more like a diamond. So what you're doing is you have control points, you're telling it to do like an outside loitering. Right. Now, have I published any of this? Only on academia. Thank you very much. A big hand for only on academia.edu. Every time I try to send these things out, they say, "Oh, this is so interesting, but it's not right for our journal." I tried philosophical journals, I tried physics journals, I tried, anyway, 5 after 5 times. That's it.
Sorry for you said this, but so in Birdsong and maybe in other physics parts of the universe, is singing down easier than singing up?
It's different than the dropping the ball because gravity is determining the speed. And we have much to say about where gravity came from and why does gravity even exist? And I will be talking to you about that. And I will be talking to you about the beginning of time and the beginning of structure. So here we go. Ready for the big leap? To the universe building assumptions. Okay, we're going to figure out how loitering is involved with the energy, how energy becomes structure and function in the universe. Before time and structure, if you think there was nothingness, there must have been sometime a somethingness. There must have been some time, but it's before time, so I can't even say that. There must have been something that appeared somehow. And that something that appeared must be in motion. It must stay in motion. Because the moment that it's not doing anything and it's not interacting with anything, it is nothing, when you think about it. It's a potential something, but...
Motion in relation to something else.
Yes, good. So all of this with the beginning of time and the beginning of structure has to do exactly with what you're saying when it becomes its first relationship with something else. If that primal energy, the thing that's somehow moving and not touching anything. If it touches something and nothing happens, it's still nothing. It's not something until it does something, until it reacts to something or causes something else to react to it. Then you got a something. Up until then, all this stuff could be going on and it's just nothing. So physics is a discipline of studying somethingness and how they interact. The godliness is not going to be part of this equation right now. However things started is going to be beyond the scope of what we can talk about. But I will show you my rendition of where things started. Can energy affect nothingness? I don't think so. And I don't think Einstein thought so either. Something affecting, let's say, gravity, affecting something else, in his case, the fabric of space-time, the something would be a structure. Where did that structure come from? I'm having a hard enough time telling you where the first structure came from. Was that structure already in place? Or did that structure all have to get in place into a neat muslin sheet that bends and folds or whatever of space-time? Or can I explain things without that fabric? And that's what I'm going to attempt to do. I'm not going to attempt to say that Einstein was wrong. I'm going to attempt to say that his relationships need explanation. I'm going to try to give an explanation for it, and that explanation is not going to use space-time. Is that where you, Bill? Okay. A guy spends his lifetime doing this kind of stuff, And I'm also going to argue that moving slowly was the first great invention in the universe. If things are always zipping back past each other, the chances of them hitting each other will be much increased if it could be slower, and the interactions that can go on and the accumulations that can go on. If things hang around, if they loiter in an area of space, you can get a buildup. Here we go into the beginning of time, the beginning of structure, the beginning of mass, beginning of gravity, an alternative to space-time, and finally, do I actually have some supporting evidence that this coil theory I'm about to talk to you about is real? And yes, I do. All right. Beginning of time, we go to Portugal. Kathy Shiovitz does this. All the other people in the class do that because that's what you're supposed to do at the tile factory. Mr. All, this is what Kathy Shiovitz does. It's beautiful. When the teacher was handing out the dry glazes back and she saw this, she said, "What's that?" And I said, I was going to try to explain to her that it's the beginning of time. but it would take about 20 minutes to do that. So I said, you're holding it upside down. And then everybody laughed, and that was it. So you see this blue line? That is energy that was moving in a straight line, and then it hit something, and it started going in that direction. And it hit something else and started going down. The things that hit are the green streams. Where are all these things coming from? You know, some people think that maybe energy was introduced into the universe and everything moved out in some sort of concentric circles. I played with that a little bit. I don't know. All I know is that if one energy moving straight stream hits something else that it reflects off of, you can begin to get time. And that is the time that it takes to go from here to here is irrelevant. Everything's all going back and forth. But as soon as you have a stream that somehow goes like that and gets to the bottom, and it took longer, if it took longer, then you have time. That's where I think the beginning of time was. The very first interaction between one energy stream and some other energy, call it a glob. Think of it as two globs of oil that are mixing and beginning of structure. If one that went down happened to go up instead, you begin to see the potential that it can close the loop. If it happened again, you could get a stream that could be moving as a coil or as some sort of circle, keep moving. This is a kind of a pre-structure. It's not really a structure. It's just the movement of energy, but I call it a pre-structure. Then, if the pre-structures somehow are able to endure, if they can just last even some sort of fraction of a second, then you could say that's a structure. It's a proto-structure. It's not really structure, but it's something that endures for a second.
Ken?
Yeah,
Can
Gary.
hi. Can you, I can't see from where I am, what are the labels on your axes? What is plotted versus what?
It's not a graph. It is something moving through the universe in any direction, meets up with something else in the universe that is also energy, and it causes the first one to change direction. I could say, oh, here's the beginning of the universe at the very top. That's the first energy. I don't know that. I don't care about that. What I care about is the reflection. So, and by the way, that was Jerry Miller. And you might have missed the part. I want to make sure everybody knows this. Jerry Miller and Jerry Pollack, who helped me so much, are not responsible for anything wrong that I say. Okay, for anything right that I say, they definitely have helped me. Okay, and so we have primal structures that are something that endures. It's just a moving energy that is taking some form other than going straight that endures. And then we get to particles. And particles or subparticles would be things that not only can endure, but they must be able to reproduce. And why do I say that? All the hydrogens in the universe, all the protons and okay, there's a couple of variations on what they look like, but basically they're made of things that must have been repeated exactly. They can't come from nowhere. And where do I get that idea? From Bill Friedman, because one time we were talking and you just happened to mention that, and that was buzzed around my head for about a year. That was an important part of this, that why do those things look alike? There must be, in the beginning of structure, some way for it to reproduce. And I'm going to show you how. The slinky. If something is moving along and some energy happens to go inside of it, this is a coil. As the energy is moving like this, always. In my coil theory, this thing moves like this. It's moving along, okay? If something happens to get inside of it, in fact, any enclosed space, it doesn't have to be a coil, but any enclosed space that could get a straight moving energy and it could reflect, and it could reflect again, you can see that if it can't get through that energy wall, it's going to follow it. And that would be how you get something just ever so slightly smaller than the coil replicating. How does it get out? Well, it could just kind of pull out, just like this thing pulls out of this thing. And then if there's just an ever so slightly expansion that went on to the interaction of the moving energy while it pulled out, you could get an exact replica of a coil. And so that's one of the reasons I like coils so much, my coil theory. Otherwise, I'd have to call it something else. So particles are the smallest structure to be able to both endure and reproduce. And I know some particles, like a neutrino, might be not as complicated as an alpha particle or something that's actually a combination of different particles. So combinations are something that are very important. But before we get to combinations, I want to talk to you about the AI thing when I was talking about how partner reflections help form structure. I was thinking that you got to wait a long time before you find things to bounce into each other. What if you could kind of contain them together so some moving energy could be always bouncing back on itself, and you get two things that are bouncing off of each other? Partners could form into structure faster than without partners. So here is Mr. Red, and he's bouncing like that, and he happens to, might have to take a longer time, but eventually he hits something else and starts coming back. Meanwhile, this other Mr. Blue finds something, he's bouncing back, and then you're going to have those two guys meet again, and again, and again, and again. And so over long periods of time, you can get structure more easily with partner reflections than without it. And that's why I think it's possible that these paired stars and now paired black holes originally arose from the advantages of being close to each other. All right, I've already demonstrated to you loitering by the slinky, but I want to tell you a little bit about coil theory and spring theory. So my idea is that this thing can reproduce and it can move through the universe and have some other wonderful attributes that I call spring theory. That is, that it, like a spring, it could be stretched out or it could be contracted. Now, why does that happen? And what's the usefulness of that in the universe? Well, there are these things that go really fast called photons, and they are going the speed of light because a photon is a unit of light. So sometimes you get a photon hitting some matter, and then the thing gives off a photon, and instantaneously it just appears and it's going the speed of light from 0 to the speed of light instantaneously. How does that happen? Well, if in matter it's contracted and out of matter it's expanded, that could begin to explain how things go fast. The other thing is, this is loitering. It's just loitering by the very fact that it's a coil. It's not going straight, it's loitering. And going slowly gives it the opportunity to be in matter and not be going the speed of light. You could actually have something in something solid that's going slow, just like that. All you have to do is that to make it go slow. So this, which I attribute to my daughter Stacy, slide for me for a talk. You have two things going really fast, and then they become coils, and they're going slower. And then what would happen if they interact? Why, they could be going so slow that they're almost not moving in space. You can begin to get an accumulation of energy in a certain area of space. You begin to get it by them going slower, but you could really get it if you have them almost not moving. That would be two coils bouncing around inside of each other, or attached, even a little bit of attachment. Bill, am I correct in understanding that the neutrino has a very, very little bit of mass? So it may be this level here is like the neutrino level, where instead of going the speed of light, and it might not be all the way together, or even it might even be kind of close together, having a little bit of mass. But I'm going to talk about, where does mass come from? I think this is mass right here. I think that when you get the movement of energy slow down so much that you can measure it, then you got mass. And we're getting better and better at measuring things, so maybe we couldn't measure the mass of a neutrino before, and now we can. That's my idea about where mass comes from. Does the word mass mean anything to you? Physics is built out of solid things that are measuring other things. So ultimately, you need to have mass involved with the energy in order to be able even to measure anything. So the beginning of time, the beginning of structure, the beginning of mass. What's gravity in Ken Shiovitz' world? Why do you think gravity exists? You wake up, you drop your book and it goes to the floor. Why is that? Why does something that has absolutely no benefit exist? We just take it for granted. Nope, it's got a benefit, got a very big benefit. That's so that Diana doesn't float up to the ceiling. That's it would be really, this is why I think gravity exists. Like any small business, you got to spend money to make money. All the heavenly bodies that are out there because whatever it is they're giving out, they're taking at least as much in. Otherwise, they'd be gone. The object is to gain material in the form of energy or anything, any other way they can get it, and bring it in. Do black holes send out energy? Yes, they do. A black hole, we have pictures of them now. This is what the picture looks like. It does. It's just amazing. So to me, it's just a coil that got bigger and bigger and bigger and bigger. And where does it send out its energy? It sends out its energy from here, from the two ends. Every once in a while, it'll send stuff out. Why is the galaxy shaped like a disc, like a tabletop? Why is it shaped like that? Why isn't there stuff on top and stuff on the bottom? Well, because it's two vacuum cleaners. One is sending stuff out and causing the other stuff to come in, and it's sending stuff out from the other end, is causing stuff to come in. That leaves the disk around, in my coil theory way of looking at it.
Nobody knows why.
You ever see a picture of the galaxy? It always looks like a spiral thing, right? They don't show it. It has a bulge in the middle a little bit, but basically it's out like a table. How is it that it's spending money to make money? What's it sending out? Some sort of emanations, right? Some sort of energy. It's probably, to me, in my way of thinking, some form of energy coil going out there, and it's probably sending it in. And why would it make money by sending it out? Suppose it hit something where all these coils were connected to each other and somehow could orient it to come in, then it would make money, right? If it would get more in than it would send out. So I'm trying to explain the emanations of bodies, and I'm also trying to explain why they happen. Now I'm going to try to tell you why I think it's how they happen. How would this planet sending out this stuff beat out these other planets and get this coil to come? Path of least resistance. Tom?
Well, if it's say sending out magnetism or something, and then the attractive bodies or forces are drawn in, is it growing or is it stable?
Excellent question about, how long things last and why they eventually are going to run out of, they say they run out of fuel. It's happening in our world today. The idea is you've got to keep the fuel going to keep the body going. Otherwise, the body's going to give out more than it takes in. If everything else is hitting this thing on the outside, and every time it hits, it's making it change its course a little bit, which way is it going to have the least exposure? Direct reaction. That's the path of least resistance. That would be why, with all the things that are coming off from everywhere in the universe, why it's going in that direction. What happens when you've got a couple coils connected and you've got a body made of a couple connected coils, got more mass? Some of these coils are going to be going, this coil is going to be going in this direction, and this coil is going in that direction. What happens when you can get them all to go in the same direction? Is it going to go faster? If these two were pulling in opposite directions, it wouldn't be going fast at all, would it? It would be stopping. In all these other directions, it wouldn't be going. But if you had them both going in the same direction, they would be going faster. And that's where I think the acceleration of gravity takes place. I think that's why the ping pong ball got faster and it went down. It's because all the coils that were making up the ping pong ball were headed in the same direction. And the closer they got, look what happens. These things are closer together here and they're further apart as they go. Get closer together, you're getting more and more orienting things. And so that would help the acceleration as well. Bill's going to say, why is it exactly the same amount? And the answer is, that's what the physicists have to work on. I don't have to answer all these questions. I'm just trying to get people to think closely in this direction to see if maybe there's going to be an experimental breakthrough on this. I'm not going to answer the question. Now, we've got 17 slides, and this is the second last one. All right, this is called lensing. It was one of the proofs of Einstein's fabric of space-time. This thing is hidden behind this other bigger body, but we can see it. It's all spoken. You can see it even though it's behind. Einstein said that it's kind of like the lensing action, that this thing's gravity is acting on space-time. It deviates light. It distorts space-time. Well, I never quite bought that, but I've seen it. I've seen a little ball go around the bowl, and it gets closer and closer and goes faster and faster. But it doesn't answer the question of what is gravity and how does gravity do that? It just says that gravity does that. You can't explain gravity by saying that gravity does this. It's not an explanation of gravity. So I came up with a different way, and I think it's just that these emanations from the planet are affecting the photons. So there's a stream of photons that's going around and it's being rerouted. Why would photons reroute around a big body? I'm going to tell you about a convoy of moving vans. We'll just take the first moving van, for example. The first moving van is coming in, and it's going to be hit more as it gets closer and closer. Those emanations are more dense. They spread out as they go further. So the front of the moving van is going to be hit more often than the back of the moving van. And just think about bean bags being thrown off from the earth, and you're going to throw that truck. Instead of going straight, you're going to start moving that truck to be going up. And then when it's right here, all the emanations are going to be about the same. But when it's there, it's going to be hit at the back of the moving van more than it's hit by the front of the moving van. And so the moving van goes back to its original course because we assume that the emanations are exactly equal. And that's what I think is happening. I don't think it's a distortion of space-time. I think it's just that Einstein couldn't think of anything else, and nobody else can. And is this something that's real or not real? Once again, we need physicists to be able to say whether it is. And finally, my last slide, is there any actual support for what I'm saying? Well, on that same chat room with Lou had the AI in the beginning of the thing, this guy named Michael Bull, he actually was the one I realized that I wrote, and he told me about Ruth Lofton's chat room. But anyway, he had a paper. In his paper, he did some math and he did an experiment. And during his math, he found that mass and gravitational field have a reciprocal relationship. That is, if one gets big, the other one gets small. If the other one gets big, then this one gets small. So that opens the possibility that a decrease in mass, that some releasable component of the mass is a component of gravity. That's just math. That's not experimental support. So what did he do that was an experiment? He built a machine. And I've given you the reference. Anybody wants to actually read his paper. And when he flowed electricity through the apparatus in one direction, he got a mass loss. And when he turned it around and flowed it in the other direction, he got a mass increase. But the weird thing was the increase was greater than the loss. And he had no way of explaining that, but it's easily explainable by coil theory. And why is that? Because if you have two coils together and you separate them apart, you've lost so much mass. And if you put them back together, you've gained that same amount of mass. But you've also taken anything else that's in the neighborhood and put them together. And so you can get more mass increase than you got a decrease. That's what I've been thinking about for the last 50 years. I'm sorry, for some of you, this is stuff that it got heavy pretty fast. Some people like the Birdsong part. Some people like the handwriting. Some people I wrote, they said, once I got through all that stuff, I got to the physics. That was the interesting part. I'll take a few questions, Tom.
Yeah. When you take the birds, the voices and all, would it divert out into flight of the birds? Any kind of connection between flight patterns and voice patterns? Flight around.
Yeah, some of them actually sing while they're fighting. In fact, the singing is the way that you don't have to fight. One time I was going down a road and there's a telephone pole. And I come to this telephone pole and I see Indigo Bunting singing his heart out. And I see another one singing his heart out. And they just wouldn't stop. And they got closer and closer. And finally, they just went like this, pecking, falling down while they're flying. And they went exactly perpendicular at the telephone pole to the road. Exactly. Like you think a territory doesn't have a line that they can see? They knew exactly where it was that they're lying. Sometimes the questions are most interesting. Anybody want to challenge any part of this is feeling like it's impossible? Diana?
Have you expanded this to other forms of writing? Like characters? I'm reading a book about Cambodia. So
yeah.
Cambodia.
I understand what you're saying. Yeah. Yeah, no, I understand. And in fact, I've challenged myself with that question. If I'm going to say something with the English language, it has to work for everything else. It has to work for Arabic and whatever. So these motions, either the straight motions or the curve motions, you just see them appearing in all sorts of things. When we were in Morocco, and the Amazigh people speak something called Tamazight. It looked like Greek letters, but what we saw were capital letters in a totally different language that completely fit this idea of having control points and going as fast as you can, either that way or that way, and versus handwritings and Arabic handwriting. That you can see all those same kind of curves. It should be explainable by control points and loitering curves. Ted?
Doctor. It's
so nice to hear that, it's been 50 years since people called me doctor.
Because this is a lot of science to get to a philosophy.
Yeah.
That when we bump into each other, or when things in mass bump into each other, and there's interaction, it's when there's meaning. It's when there's mass. It's when things begin to happen.
Well, it'd be great to take this to into the
Is that
social
where
social arena. I see where you're going.
Is that
That's-
where your brain is gone?
No, I'm afraid. I'm afraid of the amount of time it would take, but it's completely open to jump off from here to that. Absolutely, that's a great thought. Thank you, Frida, and then Bonnie.
You're no longer a person in school. They're teaching only for you. And I remember when I read it was my grandchildren, but they didn't understand personal. Is it more energy? Is you spend more time?
Yeah, thank you for asking that. You know, I have given some thought to that. If I'm calling it loitering, why does it go faster? And there's an answer to that. And the answer is the time breaks between discontinuities when you go down and then you cross the T. And cursive, all those little places where you're not putting the pencil to the paper, but you're still making the movement. Cursive is taking all those and cutting all the corners off of them. So cursive is more efficient. It's taking the corners off of the L. It's taking the, you're getting up to the T instead of going cross and then up and then down and over, you're going shortcut. So that's.
Nobody explained more on the way. Planets are making circles around the sun.
Yeah.
Which is sparkle.
Yeah. So what I'm doing is a very elementary look. If you look at the emanations from the Earth, they're not going straight out like that. They're spiraling and going around. And there was another proof of Einstein's theory that I was dealing with, and I had to take that into account, and I put that in my paper. But I can't remember exactly what I said about it. But what I did say was that after they come off, it's still a bunch of lines going in a certain direction, and you're still defining the direction to go. And as you get closer, you're not taking necessarily a direct path, but you would take maybe a curved path to get. Well, NASA is doing that all the time. It's taking curved paths to get to a straight place because everything's in motion. So, Bonnie.
Connection in your talk of Birdsong, handwriting, and the movement of black holes is loitering.
Yes.
Okay, because there's a big jump for me.
There was and this is why I think this is important, because who's going to make that jump except for me? I mean, really, it's like I see that this energy is loitering. That's why I got to the coil. How do you slow down energy? Oh, you could make it go in a circle, and oh, could that circle reproduce? And it all came from my birdsong. If I hadn't done that, okay, let's give Stephen Hawking some credit. I was reading A Brief History of Time, which is sometimes defined as the smallest book that nobody ever finishes. And and he got into a page about Darwin while he's talking about physics. And I had been out of science for probably 10 years at that time. And I read that, and I got to that page, of something like page 17, and I stopped and I said, there's no reason to read the rest of the book. I need to think about this. And I thought about that for a couple of decades before it was in my 70s. Is really, all I knew was that he had the key to putting the behavior that I studied into an evolutionary context and see that these things could evolve shapes without consciousness, but only stay because they work, just like with the bird songs. And that was the jump that I took. So in my lifetime, I don't even know if people will play with this, but I hope that I planted a seed somewhere that's for somebody to talk to somebody else and say, maybe Shiovitz had a little something right in part of it there. And anyway, so thank you for coming and listening. I'm sure that you teach the process